I'm Norman Wildberger, and welcome to this continuation of this course in linear algebra, where we're laying out a broad new foundation for this subject. Today's lecture, which is the number 24 in the series, is about cubic splines. Cubic splines using linear algebra. In particular, we're going to talk about a very remarkable approach to curves introduced by two French engineers around 1960, de Castelnau and Bézier. These are usually called Bézier curves, but Paul de Castelnau also deserves equal credit. They both arrived at roughly the same conclusions at the same time. They worked for two French automobile companies, for Renault and Citroën, and they were both engaged in trying to understand curves, like shapes of automobiles, and how we might represent them efficiently so that we can design better looking automobiles and things like that. So it's a rather interesting story because it's relatively late in the piece, 1960. As you'll see, it's a very elementary and lovely insight into curves. And it's really perhaps surprising and maybe even a bit embarrassing that us pure mathematicians didn't pick up on this a long time ago. All right, so let's start by reminding you of something from one of our first lectures when we were talking about barycentric coordinates and convex combinations. You might want to go over that video if you've forgotten some of the issues. So if we have 2 points in the affine plane, say A and B, then we can create a convex combination, or an affine combination of those 2 points, of the form 1 minus lambda A plus lambda B. Now here lambda is any number. Numbers for us are always rational numbers. And let's call this point C. Here's an example when lambda happens to be equal to 1/3. So this is the point 2/3 A plus 1/3 B. You see that it's between A and B, but it's closer to A than it is to B, corresponding to the fact that the weighting of A is greater. Indeed, when lambda is equal to 0, then we are just getting the point A. So that means that lambda equals 0 corresponds to this point here. Well, lambda is equal to 1. In that case, we get the point B, which is over here. So as lambda varies from 0 to 1, then this point C goes from A to B in a nice linear fashion. So this is a parametrization of the line segment. And in fact, that parametrization can be extended to other points on this line. So if we go in this direction, we can describe such points exactly by the same formula, but now using values of lambda which are less than 0. And if we go in this direction, well, that corresponds to values lambda bigger than 1. So as lambda goes from 0 to 1, this convex combination C moves linearly from A to B. And just to be specific, this is the kind of thing that it looks like. Suppose that A is the point 1, 2, B is the point 3, 7. I remind you that square brackets alert us to the fact that we're talking about points. Then this convex combination would have the form 1 minus lambda 1, 2 plus lambda 3, 7. And we calculate that just by working out the coordinates independently, just as you'd expect. So 1 minus lambda times 1 plus lambda times 3 makes a total of 1 plus 2 lambda. And 1 minus lambda times 2 plus 7 lambda makes a total of 2 plus 5 lambda. And if we write that as the point 1, 2 plus lambda times 2, 5, we should think of this now as a vector. This is the vector AB, the vector from A to B. I remind you that the vector from A to B is determined by taking the difference between the coordinates of B and of A. So 7 minus 2 is 5, the 3 minus the 1 is the 2. So this describes in another way why it is that this convex combination starts at 1, 2 when lambda is equal to 0. And then as lambda grows, we're just adding multiples of this vector 2, 5, going more and more and more closer to B, which is what you get when you get lambda equal to 1. So it's just a quick review of very simple, very fundamental convex combination, which allows us to parameterize a line segment. Okay? And the whole idea of these Bézier curves, the Castelao-Bézier curves, is to generalize that to higher degree curves in almost the simplest possible way you could imagine. So the very good idea that these engineers had was to consider taking a convex combination of two convex combinations. So let me explain that here in this diagram here, where we have 3 points to start with, P0, P1, and P2. Okay, and we're going to look at two convex combinations. One along this line segment here from P0 to P1, and another one along this line segment from P1 to P2. So let's define Q0 to be 1 minus T times P0 plus T times P1. You'll notice I've switched notation a little bit. Instead of using lambda, I'm using T. So you can think of T as being maybe more like time. So we're actually having a curve here. So as T goes from 0 to 1, that point goes from P0 to P1. And here this point Q1 is defined to be 1 minus T times P1 plus T times P2. So that's a convex combination of these two. And as T goes from 0 to 1, it starts here and moves linearly to P2. Now notice there's the same T involved in both expressions. So as T varies, the Q0 is moving in this direction. At the same time, Q1 is moving in this direction. So we have two different points, both traversing their line segments at the same time. All right, so we have two convex combinations. And now the idea is we're going to take a convex combination of those two. So here's Q0 at some intermediate point. Here's Q1 at some intermediate point. Actually, this looks like it'd be T equals a third, because we're roughly a third of the way along. And we're joining Q0 and Q1 and taking a point R, which is a convex combination of Q0 and Q1. In fact, R is defined to be exactly the same convex combination. It's 1 minus T Q0 plus T Q1. So if we're going a third of the way along here and a third of the way along here, then we agree to go a third of the way along here. So R is equal to, in this case, 2/3 of Q0 plus 1/3 of Q1. So now the combined effect, when we let T run, is that Q0 is moving in this direction, Q1 is moving in this direction. This line segment starts off like this and then sort of tilts like this. And while it's doing that, the point R on it runs along and traverses this curve right here, which is no longer a linear curve, it's a parabolic or quadratic curve. And it goes from P0 to P2. And the nature of things is such that when we start at P0, at first, our point R is right there, and as time starts, well, this point isn't moving very much. So the point R is really going in this direction. So the point R's initial motion is along the line joining P0 and P1. In other words, this curve ends up being tangent to the line P0, P1 at P0. And similarly, near the end of the trajectory, as we get closer to T equals 1, then the point R is coming into P2 in a tangential way to the line P1, P2. So we can say that the tangents, the tangent directions at P0 and P2 both point to P1. Notice that the curve itself does not go through P1. It goes through P0 and it goes through P2. But the P1 is not actually a point that it goes through. But nevertheless, the P1 determines the directions that this curve has at P0 and at P2. So this is a very nice way of combining two linear motions to get a quadratic motion. So which is not surprising perhaps. It's sort of linear on top of linear makes quadratic. It's a very nice way of generating this quadratic curve. Now suppose we move P1 a little bit. Well, then we would expect the curve to change its shape, but it would still be going through P0 and P2 at the endpoints. So that's a very simple kind, sort of a second degree Bezier curve. Let's have a look at how things look algebraically. So here's our formula for R as a convex combination of Q0 and Q1, and I've repeated the diagram here. Now remember, Q0 and Q1 were themselves convex combinations. Q0 was a convex combination of P0 and P1, and Q1 was a convex combination of P1 and P2. So I'm replacing Q0 and Q1 here with the corresponding expressions involving P1 and P2. The t value is the same everywhere. That t and that t, they're all the same. All right, now we can simplify things. We see that the total number of P0s is 1 minus t squared. That's the coefficient there. The total number of P2s is a t, and a t makes a t squared. And how many P1s do we get? Well, there's 1 minus t times t here, and t times 1 minus t here, for a total of 2 times 1 minus t times t. Now have a look at these three coefficients. Hopefully they look familiar. They add up to 1 because 1 minus t squared plus 2 times 1 minus t plus t squared equals 1. That's a simple application of the binomial theorem. And good exercise for you. Just make sure that you understand why that is. So prove this identity. All right, so what does it teach us? It tells us that this point R is a convex combination of 3 points, P0, P1, and P2. Why is that? Because the coefficients add up to 1, and if t is in the range 0 to 1, all these coefficients are in fact positive. In other words, greater than or equal to 0. 1 minus t squared is always greater than or equal to 0 if t is between 0 and 1. 2 times 1 minus t times t is also positive because t is between 0 and 1. And t squared is always bigger than or equal to 0 because it doesn't matter what t is. So this is a situation where this point R is in fact a convex combination of P0, P1, and P2. And we know what that means geometrically. It means that the point R is somewhere in the triangle formed by those 3 points. When t is between 0 and 1, this curve is always contained in the triangle formed by the 3 control points P, P0, P1, and P2. And the final important thing to observe is that these polynomials that are appearing here are not at all arbitrary. Hopefully you remember them from a few videos back. In Wilden Alg 21, we talked about different bases of polynomial spaces, and one particularly interesting basis that we looked at was the Bernstein polynomials. And these 3 are exactly the 3 Bernstein polynomials of degree 2. All right, so please have a look, refresh yourself from that video there on the Bernstein polynomials. They are appearing very naturally here as the coefficients of the 3 points creating the Bezier quadratic curve. So let's go up 1 dimension to the dimension that we're really interested in, which is the cubic case. So we're going to look at cubic de Castelnau Bezier curves. So how do we set that up? Well, we start with 4 fixed points. Let's call them P0, P1, P2, and P3. And here they are, P0, P1, P2, and P3. Our aim is to get a curve that goes from P0 to P3. In fact, we're going to end up with this curve here. And somehow P1 and P2 are control points for this curve. The curve doesn't actually go through P1 or P2, but P1 and P2 control the direction and the movement of this curve. All right, so how do we set this up? Well, we do almost exactly the same thing as we did in the quadratic case, but we just go one step more. So first we define a point Q0, which is going from P0 to P1, a convex combination of P0 and P1 with a parameter t. Our parameter will always be t, and it will always be going from 0 to 1. So there's Q0 going from here to here, as t goes from 0 to 1. And Q1, a convex combination of P1 and P2, going from here to here, as t goes from 0 to 1. And Q2, convex combination of P2 and P3, going from here to here, as t goes from 0 to 1. So we have these three Q points which are moving as t varies. If you imagine sliding t, then this Q slides this way, Q1 slides this way, and at the same time Q2 slides this way. So we have these 3 points, each moving steadily, starting at the same time, and all ending at their final destinations at the same time. Okay, now we create the intermediate points between the Q's. So between Q0 and Q1, we define the point R0, again, by just the same formula, the same convex combination of Q0 and Q1. So R0 is moving from here to here, as Q0 and Q1 themselves are moving. So that's exactly the same thing that we did in the quadratic case. And previously we used that point to trace out the quadratic curve. But we're going to do more this time. We're also going to have another R point, R1, from Q1 to Q2, moving along that segment. So we have now 2 R points, R0 and R1, and they're both moving along these segments, and the segments themselves are also moving. And now finally, we're going to take a convex combination of R0 and R1. That'll be S. So S is 1 minus T R0 plus T R1. And there it is there. And when T is 0, this point S is actually down here. And as you let T run, it moves like this. And as T gets to 1, it gets to P3. This snapshot that I've shown you here is the case when T equals a half. When Q0 is roughly halfway, Q1 is halfway, Q2 is halfway, R0 is halfway between these two, R1 is halfway between these two, and S is halfway between the R's. Okay, so I strongly suggest that you get out a piece of paper, draw some control points, draw some different values of T. That might be T equals a half, try T equals a quarter, T equals 3/4. See what happens to this point S and how it moves. Convince yourself that you really do get a curve that looks like this. What about the extents here? What's happening there? Well, there's nothing in the formulas that actually restrict T to being in this interval. T could also be less than 0 or bigger than 1. In that case, this formula is still going to be valid, and then the point S will trace out sort of the extension of this curve, which is like this. It's in fact a cubic curve in the plane. All right, here's an excellent exercise for you now, for your algebraic skills, to combine these various formulas to get S directly in terms of P0, P1, P2, and P3. So right here, S is in terms of R0 and R1, and R0 and R1 are in terms of Q0, Q1, and Q2, and Q0, Q1, and Q2 are in terms of P0, P1, P2, and P3. So we can substitute a couple of different levels, and then please check that this is what you get. And let's have a look at it. 1 minus T cubed is the coefficient of P0. 3 times 1 minus T squared times T is the coefficient of P1. 3 times 1 minus T squared is the coefficient of P2, and T cubed the coefficient of P3. So I hope you can see the binomial theorem popping out here at you. And I hope you recognize that these are the Bernstein polynomials of degree 3. This cubic curve that we've constructed this way, here it is here, let's call it maybe C. It has various obvious properties. It goes through P0 and P3 when t is equal to 0 and 1. And it's not too hard to see that, just as in the quadratic case, the tangent to this curve at P0 points towards P1. And the tangent to the curve at P3 points towards P2. So P1 and P2 determine the tangents to the curve at the endpoints. As I've already remarked, the four coefficients are in fact the Bernstein polynomials. B03, B13, B23, and B33. So these are discussed in Wildlin Alg 21. Please have a look if you don't remember. And they're of degree 3. That's what the second index means here. And to summarize our formula for S was a convex combination of P0, P1, P2, and P3. And the coefficients were these polynomials. Actually, they were evaluated at t, so maybe it would be better to write it this way. Sum k equals 0 to 3 using summation notation. bk3 of t times p sub k. That's also showing that, in fact, the curve, when t is between 0 and 1, then each of these quantities is always positive, and they add up to 1, just as in the quadratic case. So the curve necessarily is in the convex hull of now 4 points. The 4 points P0, P1, P2, and P3. So if we draw a box, that solid box formed by those 4 points, the curve always lies in that box. These kind of cubic curves, the de Castelnau-Bézier cubic curves, are of great importance these days in design. And that's how and why they were initially introduced, to help in the design of automobiles. Because both de Castelnau and Bézier worked for automobile companies. So here perhaps is a new model of a new French car. And it has a lovely shape here that some artist has worked very hard to accomplish. And we would like to encode mathematically this shape. So we can send it to engineers in other parts of the world. It's just over the internet perhaps. And maybe we don't want to take a picture, we just want to encode some finite amount of data. So the idea is that we're going to divide the curve into reasonably manageable pieces, relatively simple arcs. So these cubic curves are good for describing arcs, relatively simple parts of the curve. So even if the curve is relatively complicated like this, we can subdivide it into pieces, each of which piece is relatively simple. Let's have a look at this piece here. We've divided it with these 2 points here into this arc. Let's blow this arc up. Here are the 2 points. Okay, so the idea is that what we should do is we should try to find the other 2 control points. So this would be P0, that's P1, that's P2, and that's P3. So that the de Castelnau-Bézier curve that's associated to these 4 points is the actually curve that we're looking at in this diagram. So if we have a little computer and we can move these points around and adjust, well, then we can physically move them around and visually get this curve oriented to the shape that we want it to. And then we can record the position of these 4 points, and that encodes that entire arc. Right? So these 4 points end up encoding that arc. What I have to do is transmit these 4 points to you, and then you can easily recover that arc using the formula involving the Bernstein polynomial coefficients. All right, so that's the basic idea. It's very simple and elegant. We cut the piece up into manageable little arcs, and for each little arc we create a Castelnau-Bézier curve by finding control points so that we're accurately capturing that piece of curve. And for that, it's helpful to remember that basic rule that the control points here, these black ones, are going to lie on the tangents to the curve at the other 2 control points that are actually on the curve. So if a designer came to a board meeting and the board said, well, that looks pretty good, but can we just change the shape of that a little bit? Can we just maybe move the curve down a little bit? The engineer doesn't have to recompute some elaborate equation. He just moves these control points a little bit and the curve adjusts its shape. Okay, and it's pretty easy to drag and drop. If you have a design program like CorelDRAW or Adobe Illustrator or something like that, they will have Bezier curves in them, and you can play around and experiment with the control points and move the curves around. It's a pleasant thing to do. So it's a very efficient way of encoding arcs, very efficient way of encoding curves for careful design work. So this is a really lovely idea, and indication of why it's so nice is that it extends very nicely to higher degree curves. So it's no big conceptual jump to introduce a few more control points and get a little bit more sophisticated behavior, but it's still essentially exactly the same idea. So here I've shown you a quartic curve, this blue thing here, which is generated by 5 control points. P0, P1, P2, P3, P4. And you can see that I've got points Q0, Q1, Q2, and Q3 on those segments. And then the segments formed by the Qs, I've got R0 going here, R1 going here, and R2 going here. And then between the R's, we have S0 along here and S1 along here. And finally, T going from S0 to S1. And it's this T, its movement, as all of these things move along their segments, as T goes from 0 to 1. The combined effect is that T will move on this quartic curve given by a 4th degree equation. So the more control points that we have, well, the higher degree curve that we get. And it's not too hard to see that the lovely formula involving the Bernstein polynomials extends very naturally. So we're just getting higher degree Bernstein polynomials, and it's somehow very natural and pleasant. So this certainly gives us more control over curves because quartic curves are more flexible than cubic ones. But there is an additional complexity because now you have these 3 control points to move around, and it gets a little bit more complicated. So in practice, it's actually quite reasonable to stick to cubics. Cubics give us enough flexibility to be able to model any reasonably simple arc. And if we have a complicated curve, we'll just cut it up into little arcs and approximate each of those little arcs with a cubic. So in general, cubics suffice for most of these approximation problems. And I might just add that there's another important direction where we go to 2-dimensional analogs, which is, of course, can be also very important for modeling a car or an aircraft or something like that. So we have these so-called Bezier surfaces, where basically we do the same thing but in 2 dimensions at the same time instead of 1. Okay. Once you've understood the 1-dimensional case, the Bezier surfaces are not too much of a jump. I'd like to finish by saying just a few words about the kind of cubic curves that are generated by this process of de Castelnau and Bezier. So quadratic curves are reasonably well studied in high school. We all know that they're conics. They're conic sections, ellipse, parabolas, hyperbolas. That's the range of conics or quadratic equations in the plane. Cubic curves, however, have more variety. There's more different kinds of cubics. And here are very familiar pictures that you see in many books of different kinds of cubic curves that can arise. So these are curves generated by equations, polynomial equations of degree 3 in x and y. So we can get a curve that looks like this, sometimes called an elliptic curve, or one like this that has a kind of a cusp, called a cuspidal cubic, or one that goes like this that we've actually seen in our example, that's a nodal cubic. These are actually rather standardized form. In practice, if you were actually write down a random 3-degree polynomial, then it's likely not going to look at all like this. It'll look maybe more something like this. So here's an example of another version of the elliptic case where it looks like there's sort of three hyperbolic branches. But in fact, you should think of these branches as sort of connecting. So this one here connects with this one at infinity, and this one connects with this one at infinity, and this one connects with this one with infinity. So there really is only one other branch beside this little blob. So it's really not that much different from this one if you think projectively. Don't worry if that didn't make too much sense. Okay, so the point is that the cuspidal and the nodal cubics are the ones that can be rationally parametrized. There's a big difference in the cubic world between the cuspidal and nodal cubics and these elliptic ones. These ones are much simpler, and these are the ones that are appearing in this Bézier curve business. We don't get elliptic curves, because if we did, then we could parameterize them. The de Castelnau-Bézier process is actually parametrizing the curve, because it's associating to each point on the curve the parameter value t. And it's doing so in a very rational way, because it's just a combination of various affine motions. So in fact, there's some connection here with algebraic geometry. We're finding rational parameterization of cuspidal and nodal cubics using this point of view. Okay, so there's another aspect of cubic splines that I'm going to talk about next time. It's related to this, but it's going back to more a calculus point of view where we have a number of data points and we want to connect them with a nice curve. So we can basically apply the same principle here, the idea being that we should think in terms of little cubic arcs between adjacent points. Well, that's more of a calculus approach next time. We're still going to be thinking about cubic curves and splines in terms of approximating functions. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.